Hi everyone. Is the audio clear now? Tell me. So let's start now. Uh, in this lecture, we will study disk management, free space disk management. So in the disk, you have space, a lot of space you have. If your disk is 1 terabyte, 2 terabyte, so you have a lot of space in the disk. Now, how to manage that space? Because your RAM, your main memory is very small, like maybe 4 GB, 8 GB. But your this memory, your disk, your hard drive, that is very big, 1 terabyte, 2 terabyte. Okay, so how to manage that space, that is that topic we want to study. This topic you have already seen in the operating system, but anyway, let me tell you that this topic is also in DBMS. This topic is also in operating system. So you have already seen this topic in the operating system, like the methods, how to manage the free space, like the bitmap and linked list. So those two methods you have already seen, right? Correct. Okay, so there are two method. One method is bitmap, another method is free list, which is basically the linked list. Okay, so this topic actually you have already seen in the operating system, but what I want to do, I want to solve some questions. Okay, actually, because there are some good questions from this topic, so those questions I want to solve. Okay, so this lecture, it is going to be like a revision, because in the operating system you have already seen what is this disk space management, how to manage the free space. So that topic you have already seen in the operating system. So mostly what I will do, I will take a lot of questions. So what I have done, from the internet, all the questions that I found, all those questions I have taken. So you take your copy pen. Okay, take out your copy pen, and those questions we are going to solve. Let me tell you that on the internet there is no other question. Okay, like all the questions from the internet I have taken. So from this topic you will not find any other question on the entire internet, in the standard resources, on the check website. All the questions I have already taken. Okay, so let's solve these questions now. Let me do some revision also. So basically in this lecture we will see, first we will see disk space management, then we will see how to keep track of free blocks. Okay, like which space is free, where is our space free. Okay, so that also we will see, keeping track of free blocks. And we will see, so to keep track of free blocks, there are two methods. Free space management, there are two methods. One is bitmap, another is free list method, that is linked list method, right? Okay, so these two methods we are going to see now. Let's start. So yeah, let me start with disk space management. You have a lot of space in the disk, how to manage that space, right? Correct. Okay, so now let's see that. So let's start with this topic. So you already know that files, whatever files you have, that you store on the disk, and file is divided into what? Can anyone tell me? File, any file that you have, that you store on the disk. From the DBMS point of view, what is a file? From the DBMS point of view, file means relation, right? From the DBMS point of view, you can notice this file simply means relation. So if you see from the DBMS point of view, from the database management system point of view, from the database point of view, okay, from the DBMS software point of view, this file is basically a relation. It is a relation. Okay, and you know that this file is divided into blocks. So this is your file, and this file, what we do, this file is divided into blocks. So this is your block B1, this is your block B2, and this is your block B3. So this is divided into blocks. Okay, very simple. So from the DBMS point of view, remember, file is a relation. From the operating system point of view, file can be anything. Correct. Okay, from the operating system point of view, this file can be anything, like your movie, your photo. Okay, this can be anything from the operating system point of view. But from DBMS point of view, what we do, so for every relation we create one file. Okay, so this file means relation, and we divide this into blocks. And this is a block, right? This is a block, and this block is basically nothing but this we store on the disk. What we do, we store this block we store on the disk. And this block is nothing but a consecutive sectors, right? Okay, so DBMS will decide what is the how many sectors we have to take. Okay, so that is fixed. Basically, block size is fixed. You already know that all the blocks, they have the same size. So block size is basically fixed. Okay, So either you can take one sector as a block, or you can take two sector as a block, three sector as a block. That is your choice. So block size is basically fixed by DBMS. Fixed by DBMS. Okay. Now let's see the next. So here you can notice files are stored on the disk. We store the files on the disk, and the management of disk space is very important because you have 1 terabyte, 2 terabyte space, a lot of space you have. So the management of that space is really a major concern for the designers. Okay. So you know that file is already split into a number of blocks. And remember one more thing I want to tell you, that tell me one thing. Like, let me assume that you don't have 3 consecutive blocks available. Then what to do? Let me assume that you don't have 3 consecutive blocks available in your disk, in your hard drive. 3 consecutive blocks are not available. Then remember, these blocks are like, you can store them in non-consecutive blocks also. Okay, it is not a mandatory thing that you have to take the consecutive blocks. Are you getting my point? So to store this file, it is not mandatory. It is not mandatory to store. I can say it is not mandatory to store this file in consecutive blocks. For example, this block B1, maybe this block B1 you can store. Then this block B2 you can store. Maybe this block B3 you can store in another cylinder. Okay. So remember, wherever you find the space, you can store that. Okay. So like that you can do. And what we can do, like for example, if I store this B3 not consecutively, if I store this B3 in some other cylinder, tell me then what I will do. If I store this B3 in some other cylinder, then what I will do? Then this pointer, there will be a pointer in the block header. There is a block header, right? In every block, there is a header, right? Correct. So in this block header, I will put the pointer of B3. Is this clear? Okay. So this is your block header. This is called, what is this? This is your block header. So in the block header, I can put the pointer of the next block. So here I can put in the block header, I can put that, okay, this pointer I can put. This pointer I can put in the block header. Okay, so like this. Anyway, so what I'm saying is that this file you break into this file, you break into blocks. Okay, but in your hard drive, in your hard disk, it is possible that you don't have consecutive. For example, let's assume you want 20 blocks, but let's assume 20 blocks are not available consecutively. Then what you can do, you can store them anywhere. Okay, wherever you get the space, you can store them. So file you split into a number of blocks. Okay, either if possible, remember what we will do. If possible, we will take the contiguous block, right? Agree or not? Okay, if possible, if it is possible, okay, like if the contiguous blocks is if this is available, then of course we can take it. But it is not a necessary thing. It is not a necessary thing. This is what I'm saying. It is not a necessary thing. If you find the space anywhere, you can store. You can store one block here, another block here, another block here, another block here. So you can do that. There is no problem. Okay. So this is the idea. Now, so all the file system, what they do, they chop up the files into fixed size blocks. Okay. That need not be adjacent. That need not be adjacent. Okay. So this is the point. Now let's move on. Now you tell me this question. This is a question actually. Block size issue. How much block size we should keep? Again, hard drive is not deciding the block size, right? Correct. Yes or no? Hard disk is not deciding the block size. So the hard disk manufacturer, he is not going to decide the block size. He will decide the sector size. He will decide the track size, platter. Okay. The hard disk size, he will decide. But you can notice that the block size will be decided by the DBMS. So this DBMS, of course, this block size is I can say this block size, this is decided by the DBMS. So this block size, okay, the DBMS is decided by DBMS. Decided by DBMS. Okay. Now, you can easily see that how much I should decide. Tell me how much I should decide. How big the block should be. You tell me simple point. If it is less size, then what will happen? Just tell me a simple question I'm asking, a very common sense question I'm asking. If your block has a small size, if you are having small size block, then what will happen? If you have small size block, then a lot of memory will be wasted, right? Sorry. If you have small size block, then a lot of blocks will be there. Correct. If you have small size blocks, then a lot of blocks will be there in your file. When you divide your file, then a lot of blocks will be created. You can easily see. So if you have a small size block, if your block has small size, a very simple point. If your block is small, then what will happen? Your file will contain many blocks. Agree? your file will contain a lot of blocks. Okay, so for any desired data, if you want to access some data, then you have to access more blocks, because the transfer will happen block by block. Agree or not? The disk access will happen, the disk transfer, if you read or if you write, that will happen block by block. So if you have more number of blocks, your file is divided into more number of blocks, then to access some data, okay, you will access more number of blocks. Correct, right? So that is the reason I can say time will be wasted, a lot of time will be wasted if you have small size. So if your block size is small, then a lot of time will be wasted, I can say. Correct or not? A lot of delays will be there, a lot of time will be wasted. But if you have large size block, then what will happen? If you have large size block, then what will happen? Like block size is very large, very large. Now what will happen? Now if your file is very small, then this space will be wasted. Agree or not? See, your block size is very large, let's assume, and your block size is let me assume that 20 sectors. You are saying that 20 sectors is my block size. Okay, 20 sectors is my block size, but your file size is one sector. Then a lot of space will be wasted. Okay, correct? A lot of space will be wasted. Okay, in your hard drive, a lot of space will be wasted. And I can ask you one more point. From the hard drive point of view, of course, space also matters, because like in your computer, if a lot of space is wasted, you don't want that. Okay, you will not use that computer if a lot of space is wasted. Correct? Okay, so what I'm saying is very simple, that if you have large size block, okay, then what will happen? Then in this situation, even the small size even the small size file, even a very small file will take a lot of space. If your file is only 1 byte, if your file is only one sector, that will also waste a lot of space. So it will waste a large amount of space. So this is the complete point. So finally, this is the conclusion we can give. What we can give? So if you have a small size block, then what will happen? Then there will be many blocks. Your file will contain many blocks, correct? Every file will contain many blocks. And if every file is containing many blocks, then it will take a lot of time to disk access will happen block by block. If you read, then you will read a block. If you write, then you will write a block. So disk transfer, disk access, that will happen block by block. So a lot of time will be wasted if you have small size block, and a lot of space will be wasted if you have large size block. So this is the final conclusion. What is that? This is the final conclusion, that if your block size is large, then space will be wasted. If your block size is small, then time will be wasted. So you need some trade-off, right? Correct? Okay, so I can say some middle point we have to find. So some middle point, remember, some middle point we have to find. So some middle point we have to find, of course. Okay, so some trade-off, maybe you can find maybe 4 KB, or some middle point we have to find. Okay, now let's see this. Now let's see this one. Let's solve this question. Tell me what is the answer. A very easy question. Consider a disk with 1 MB per track. On one track you have 1 MB. Okay, 1 MB per track. A rotation time, one rotation is taking, you can notice a rotation time is 8.33 millisecond. Next, Mavit is saying minimum block size should be such that to hold one file. No, array Mavit, file is divided into blocks. So like it is not necessary. Your file can be very big. Your file can be very, very, very big. Okay, maybe your file is maybe your file can be 20 MB and your block size is only maybe 10 KB. So your file is divided into blocks. Is that clear? This we have already seen, that you have the file, this is your file, and this file will be divided into blocks. Now we just want to make sure that your block is not too large, your block is not too small. Is this clear? Your file is very big. Your file can be small also, your file can be small also, your file can be big also. Now what we do, this file, okay, we divide into blocks. We have to decide that this block should not be too large, should not be too small. If this block size is too large, if it is too large, then a lot of space will be wasted. If it is too small, if this block size is too small, then what will happen? A lot of time will be wasted. Okay, now let's solve this question. So tell me the answer here. So a disk has 1 MB per track. A rotation time is taking 8.33 millisecond. And average seek time is average seek time is already given to you. That average seek time is taking 5 millisecond. The time in millisecond to read a block of k bytes. So the time in millisecond to read a block of k bytes. What the answer will be? The answer will be average seek time. Okay, correct. Okay, your average seek time is 5. That is already given to you. That is average seek. That is average seek plus half the rotational time. Half of rotational time. This is one rotational time. So this is your average rotational latency. This is your average latency. Next, plus what you will do? You can easily say that 1 MB you can transfer in 8.33 millisecond. Agree? Yes or no? Correct? Okay, so 1 MB you can transfer. 1 MB you can transfer in 8.33 millisecond because that is the size of the track. So how much you will take for k bytes? For k bytes, how much you need? So in one rotation, you can transfer this much amount in one rotation. Okay, in one rotation, you can transfer this amount of data. So k byte, for the k byte, what you need? So for the k byte, you need basically, I can say that 8.33 multiplied by k, these many millisecond. Okay, divided by what you will do? Divided by 1 MB. Okay, 1 MB. So here you can notice. So one byte will take this. For 1 byte, you can find the time. For 1 byte, you can find the time. And then what you can do for k byte, you can find the time. So this will be the time. Okay. So your answer will be very simple. This is your answer. 8.33 k millisecond divided by m. So that will become basically k. That will become 1000. K bytes. Okay. So that will be k. That is your 2 power k. 2 power. Remember, this is actually data, k bytes. Okay, so this will be actually 2 power, it will be 2 power 10. Is this clear? Okay, so because you can cancel this. So remember, this k is basically 2 power 10. This m is basically 2 power 20. Okay, this m is 2 power 20. So this is going to be your answer. Yes or no? Is this clear? Okay, tell me. Anyone has any doubt in this? Is there any doubt? Let me know. Okay. So this is the final answer because this 2 power 10, 2 power 20. So you can cancel it. In the bottom, you will get 2 power 10. Okay. This is millisecond. So your final answer will be in the millisecond. So this data you can add. This data you can add. This will be your final answer in the millisecond. Okay. So quite simple actually. This is a very simple question. Now, let's see. So actually, this ambiguity you will not find in the GATE exam. See, this is ambiguity, of course. Like this is ambiguity, like whether to take 10 power or 2 power. Okay, you will get a very close answer because 2 power 10 is 1024 and 1000 is 1000. Okay, so you can notice you will get a very close answer. You will get, and in the GATE exam, what they will do? They will give a range. Are you getting my point? Okay, they will give a range. So far in the GATE exam, it has never happened that because of this ambiguity of M or K, some student has lost marks. It has never happened. Are you getting my point? So far in the GATE exam, it has never happened. It is never that because of this. Okay, what should I take? What should I take? This k should be 10 to the power 3 or 2 to the power 10. Okay, so because of this ambiguity, you will not lose marks because in the GATE exam, what they will do? They will create a range. They will create. Like if your answer is, for example, if your answer is 2.25, then they will give a range. They will give a range like this, that 2.23 to 2.27. Are you getting my point? So in the GATE exam, they will give a range. Okay, so you don't have to worry about this ambiguity. But anyway, we will stick to this. What we will stick, because for the data, we will stick that this is basically 1. I can say we will stick to 2 to the power because this is 1 MB. Array, this is data, right? Yes or no? So this will be like 2 to the power 20 bytes. This is 2 to the power 20 bytes. Okay. And finally, this is k bytes. Oh, sorry. This k is not that k. Okay, okay, okay. This k is not that k of k bytes. Okay, so sorry. This k is not that k. Like this is some x. Okay, this k is some x. This k is some x. How to read k bytes? Okay, so this k you can consider this k as some x or y. Okay, like maybe you can consider this as a y. So how, okay, for y bytes, how much space? Okay, sorry, this is not that k. This is a variable. Yeah, right. Okay, so this is a variable. You can call it y just to confuse, just to avoid the confusion. Okay, actually in the question, if you read, this is not, this is a k byte. You can take this k as a y. You can take this k as a y bytes. There is no problem. Okay, so yeah, this is not a kilobytes. It's not 2 to the power 10 bytes. Okay, this is k. This is just a random number. So your answer will be something. Your answer is going to be 8.33, okay, millisecond divided by 2 to the power 20, okay, y. This will be your answer. Okay, is this clear? Okay, so quite simple. Actually, the question is quite simple. And remember, because of this ambiguity, you will never lose marks. This I am telling you again, because some students, they worry too much. Like, sir, should I take m equal to 2 to the power 20, or should I take 10 to the power 6? Okay, because of this ambiguity in any subject, whether you take computer network, whether you take computer organization, because of this ambiguity, you will never lose marks. But still, what we can do? Okay, this assumption we take that for the data, we whenever data is involved, then this is a very common sense that if data is involved, it is a very like common sense that if I tell you 1 GB, okay, then automatically what will come to your mind? Automatically this will come to your mind, right? Okay, so this will come to your mind. And if I say that whenever I talk about time, for example, if I say 1 millisecond, okay, 1 millisecond, then automatically what will come to your mind? This will come to your mind. Okay, so remember, because of for data you can take this, and for I can say for time you can take this. Is this clear? So anyway, we stick to this convention. But remember one more thing I am telling you, because of this ambiguity, you will never lose marks. Okay, because of this ambiguity, you will never lose marks. Of course, you can lose marks in the test series, but you will never lose marks in the GATE exam, because in the GATE exam, they will give you a range. Okay, because in the GATE exam, your answer will have range. Okay, now let's move on. So here actually you can take this, not this, you can take very simple 2 to the power 20. Now let's move on. Now, keeping track of free blocks. How to keep track of free blocks? You have some free blocks. How to keep track of them? So because your disk space is, of course, disk space is limited, you don't want to waste it. Okay, so you want to keep track of free blocks. For example, if I want to create a new file, then what I need? I am creating a new file. Then I need free space, right? So how to keep track of free space? There is a lot of space in the disk. In your hard drive, you have 1 terabyte hard drive. There are a lot of blocks. There are many number of tracks per cylinder. Okay, there are many cylinders, there are many sectors, there are many blocks. So in your hard drive you have many blocks. You have, okay, billions of blocks you have. Then whenever you want to create a file, you are creating a file, then how to find out the free space? Are you getting my point? How to find out the free space very quickly? You have to find the free space, you have to find it quickly. And if I delete a file, then you have to add this free space in your free space list. Yes or no? Basically you are maintaining the free space, that this is my free space. Now if a file will be deleted, then what you will do? If this file is deleted, then this space will be added to this free space. Okay, this is your free space, and if a file will be deleted, then this space will be added to this free space list. Okay, so now let's solve this. Let's see this. So if you have free space, then how to keep track of free space? Now, free space means it is not allocated to anything. Okay, free space simply means that it is basically free disk blocks. Okay, and it is not allocated to any file. There is no file which contains which is stored in these blocks. Now there are two methods. Remember, you have two methods. One is bitmap, or you can call it bit vector. There is another method that is linked list method, or you can call it free list. So there are two methods. You can call it bitmap, bit vector. You can another method is linked list, or you can call it free list. So there are two methods to keep track of free blocks. Where are the free blocks? Okay, so the first method you already know, that is bitmap. In this bitmap, what we do? For every block, we create a bit. Either a block is free, either a block is, this is a very obvious method, because whatever block you take, either it will be free or it will be occupied, right? So either it will be free or it will be occupied. Now, in this method, what we do? In this bitmap method, what we do? Let me assume that, consider this scenario. Let's assume that this is free. Let's assume this is free. Okay, and I'm starting the counting here. For example, let's assume this is your block 0. Okay, this is your block 1, this is your block 2, this is your block 3. Okay, this is your block 4, and so on. And so on, your counting is going on. Okay, this is your block, you can notice this is your block 5. So this will be block number 8, and block number 11, and block number 14. Correct? Okay, so these are your block numbers. Now let me assume that this is free. Let me assume 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 this is free. And let me assume this is free. Okay, all other are occupied. Is this clear? So F simply means free block. F simply means what it means? It means a free block. You have a free block. It means free block means no file. It contains no file. Okay, free block. This is a free space. Okay, so I can say this is a free block space. Now you tell me, so how to keep track of this? So total you have how many blocks? So total you have 15 blocks. Correct? Okay, I am taking this example where you have total 15 blocks you have. So in this example, total 15 blocks you have in this disk. This is your disk. Here you have 15 blocks. Now, what this bitmap method says? This bitmap method says that for every block, either it is free or it is busy, right? Correct? Either this will be free. Whatever block you take, either it will be free or it will be busy. Okay, right? Correct. So what you can do, this bitmap method, it says that what you do, if it is free, because our concern is free or busy, you tell me one thing. Our concern is free or busy? Our concern is free. We want to find the free blocks. Okay, so remember, our focus is on the free blocks. So what I do, okay, on which our focus, on this our focus is, so very naturally we denote this by 1, and we, if it is busy, if it is occupied, then we denote by 0. If it is occupied, then we denote by 0. Is this clear? Because our focus is on the free space. Okay, is this clear? So remember, this is by default. Of course, I will also tell you that what you can do. You can also do this. That if it is free, then you use 0. And if it is occupied, then you use 1. This is also valid. This also can be done. Okay, remember, this also can be done. This also can be done. But which is better? Tell me, which is better? Or I can say which is by default. Which is by default? So remember, this is by default because our focus is on the free space. This is by default. If no information is given, then you can take it as by default. Is this clear? If no information is given, you can take it as by default. You can take this as by default, you can take. But remember, okay, this also can be done. This also can be done. Okay, this is also correct. So both are correct. Is this clear? So don't think that this is not correct, this is correct. Okay, so remember, this is by default if no information is given. If in the question there is no information given, then you can take this, that free block you can represent by 1, and this occupied block you can represent by 0. Okay, so by this convention, this is a convention. By this convention, what will happen? So for every block you will store like this, that this block 0, this is free, so you can call it 1. Then block 1 is 0, block 2 0, block 3 0, block 4 1, then 0, then 0, then 0, then it will be occupied, then 0, it will be occupied, free, then it will be 0, then it will be 0, then it will be 1 1. So your answer will be this. Are you getting my point? So you will store like this. You will, in the bitmap method, this is a bitmap method. In the bitmap method, you will store like this. Okay, tell me, is this clear? So basically this data you will store in one block, of course. So this bitmap method says that this you will store in one block, stored in a block. And that block where you will keep, tell me. This will be stored in a block. This is giving you what information? This is giving you information about the free space, right? Yes or no? This is the free space information, correct or not? This gives you the information about the free space. So this is free space information. Okay, so this is free space information this is giving you. So where you will put it? So this you will store in a block, and this block where you will put it, and this block we will put in the main memory so that we can quickly find out. Okay, this we will put in the main memory. This block we will put in the main memory buffer. There is a main memory buffer, right? I told you in the main memory there is a buffer. Okay, there is a buffer, so there you can put it. Okay, so this information will tell you about the free space. Whatever free space you have, this information will tell you. Okay, then what you can do, this information you can store in one block, or maybe one block, two block, that depends on your size of block. Remember, yes or no? This information you can store in one block or two block. That depends on what is the size of the block and what is the size of this information. What is the size of this information and what is the size of block? Depending on that, this information you can store in one or more than one block. Either one or more than one block you can store, and then you can store them in the main memory so that you can quickly find out the free space. If you create the file, if you delete the file, you can quickly find out the free space. Okay, so that is the reason this block, this bitmap block, I can call it bitmap block. This bitmap block you store in the main memory. Is this clear? Let me know. Of course, you can do this also, that free is 0 and occupied is 1. Then in this situation, your bitmap will look like this. Okay, 0, 1, and then you can notice. Okay, so 0, 1, 1. So you can do like this: 0, 1, 1, then 1, 0, 1, then 1, 1, 0, then 1, 0, 1, and then what will happen? 1, 0, 0. Okay, so your bitmap will look like this. Again the same thing. This you will put in one or more than one block. This information, what you will do? This information you will store in one or more than one block. In one or more than one block. Because remember, it can happen that this information is very large. Okay, because you can have a large number of blocks. If you have 1 billion blocks, then what will happen? Tell me. If you have 1 billion blocks, then there will be 1 billion bits here. Correct? Yes or no? Agree? So if there are 1 billion blocks, there will be 1 billion bits here. So it can happen. It is possible that this information takes a lot of space. It can happen. It is possible that this information you cannot store in one block. So it is possible that you have to use more than one block. So either you use one or more than one block to store this information. This is your bitmap method. Very simple method, right? Correct? Okay. So this is the idea. For example, here you can notice, like if you consider a disk where block number 2, 3, 4, 5, these are free. Then what will happen? Because these are free, so we are using one. For free, we are using one. Okay, so block number 2, 3, 4, 5, these are free. Then in this question, you can notice 1, 1, 1, 1. Okay, then you can notice 8, 9, 10, 11, 12, 13. Okay, 8, 9, 10, 11, 12, 13. So you can use this. So like this, you can use this bitmap method. This is a very simple method, right? Okay, so like this. And remember, this bitmap, whatever is your bitmap, you can store into blocks. One block or two block, depending on your bitmap information. How much information is this? How big is this information is? Depending on that, you can store this information in one block or more than one block. Okay, so you can notice in the bitmap method, a disk with n block will necessary. It is necessary. Tell me how many bits you need in the bitmap. Tell me how many bits you need in the bitmap. So if you have n blocks, then n bits you need. Does it depend on the free blocks? Does it depend on the free blocks? Does it depend on the free blocks? No, it does not depend on the free blocks. If you have a disk with n blocks, then definitely you need n bits. Okay, free blocks are represented by 1 and the remaining blocks are represented by 0 or vice versa. Okay, so very simple. The main advantage, what is the advantage of this approach? What is the advantage of this approach? That is simplicity. This is very simple. Okay, and there are many things you can do. If I ask you to find consecutive 6 blocks, then very easily you can find. Agree or not? If I ask you to find consecutive 6 free blocks, consecutive 6 free blocks, you can very easily find. Okay, in this approach, very easily you can find the consecutive 6 free blocks. And if I ask you find the first free block, then that also you can ask, right? I can call it first free block. See, if you want to find first free block, that also you can find. If you want to find consecutive free blocks, that also you can find. Okay, so like I can say these are the consecutive 6 free blocks. Consecutive 6 free blocks. Okay, so if you want to find the consecutive blocks, that also you can find. And if you want to find the first free block, that also you can find. Okay, so like this you can do. So all these things you can very easily do. So this is the approach. This is the I can say. Now tell me the answer for this question. You have 1.3 GB disk with 512 byte blocks. The system uses bit vector to allocate disk space. Okay, so you have 1.3 GB disk and you are using a bit vector to allocate disk space. What is the size of bitmap? Tell me the answer for this question. A very simple question. What is the size of the bitmap? So the bitmap size is very easy to calculate. First of all, you calculate number of blocks. Okay, so number of bits, you already know this. What is number of bits in bitmap? In the bitmap, how many bits you have? In the bitmap, how many bits you have? That is number of blocks. So first you find out number of blocks. So what is your number of blocks? What is the number of blocks? This is the disk. Okay, and 512 byte block you have. So your disk is 1.3 GB divided by 512 byte, this block size you have, right? So how many blocks are there? So number of blocks, that will be what? That will be 1.3 multiplied by 2 to the power 30 bytes divided by 512 bytes. 512 is nothing but 2 power 9. That is 2 power 9 bytes. So your answer will be 1.3 multiplied by 2 to the power 21. These many blocks you have. So these many bits you have. So I can say number of bits in bitmap. In the bitmap, how many bits you will have? In the bitmap, these many bits will be there. Remember, these many bits will be there. These are the blocks. These many blocks you have and these many bits you will have. Now this data is in the bits and we have to find the data. Of course, the answer will be given in the byte. They are asking the size of bitmap. So what is the size of bitmap? You can find the size of bitmap like this very easily. So you can say that into 2 in the bytes, maybe you can find the data. So if you want to find the data in bytes, then what you will do? Then you can write like this: 2 power 12, 2 power 18, 2 power 3 divided by 2 power 3. You can write like this, bits. Now this will become byte. Okay, remember this will become byte. So finally your answer that will be, now you can find the answer is MB. If you want to find the answer is MB, then you have to multiply with 2 power 2 divide by 2 power 2. Or maybe you can find the answer is KB. Okay, if you want to find the answer in KB, that what will be? That will be 1.3 multiplied by 2 power 8. This will be your answer. Okay, so can anyone tell me what is this value? Can anyone tell me what is this value? 1.3 multiplied by 2 power 8 KB. You can find the answer in KB. So your answer will be what? That is KB. 1.3 multiplied by 2 power 8, that is 256. So 1.3 multiplied by 256. What is that? So you can calculate. I think it will be around somewhere here. 332.8. Okay. So it will be 332.8. So this will be your answer. Somewhere like 332 KB. Almost 332 KB. Okay. So this is going to be your answer. Is this clear? Very simple, right? Because remember, this is the fact that number of bits in the bitmap, that will be equal to number of blocks. Okay. Very simple. So just find the number of blocks. Those many bits will be there. Those many bits will be there. This bit you have to convert into byte because the answer will be given in the byte. They can give you the answer in the byte, remember. So this bit will be there. This bit you can convert into byte very easily. Okay, let's see this question. Tell me the answer for this question now. Assume that only 1 MB free space is there. Will this information change anything? Will this information change anything? So this information does not change anything. Okay, this information does not change anything. Okay, this is just to confuse. Yes or no? This information can confuse some students. Some students can get confused by this information. Oh, okay, free space is given. Okay, I have to do something. Because the information is given in the question, I have to use it. Okay, so of course. So very simple, remember, just because some information is given in the question, it does not mean that it is useful. Your answer will be same. Your answer will be 332.3 kilobytes. Your answer will not change. 332, okay, 0.8 kilobytes. So the answer is not going to change. Okay, let's move on. Now, the next method is linked list, right? This is the next method. Before this, actually, one more variation we can create. Let me tell you, one more variation we can create in the disk. This one more variation in the bitmap. One more variation can be created. Variation in bitmap. This type of variation also can be created. This is a standard variation. In the bitmap question, what variation they can create? This variation they can create. Okay, I'm just giving you the heads up. Like if by chance some question comes, then you can handle it. This is a standard variation in the bitmap question. Like if you have, let me assume that, for example, let's assume that you have 16 blocks. Is okay. Let's assume you have 16 blocks. So those blocks are maybe from B0 to B15. These are the blocks. These are the blocks that are given to you. So automatically your bitmap will be what? Your bitmap will have what? That will have 16 bits, right? So that will have 16 bits. Now, remember, if this is given to you that one word means 4 bit. Let's assume this is given that one word means 4 bit. One word means 4 bit. Okay, or so this pattern will be given to you, correct? Okay, so I basically this whatever is this, I can convert it into words. Let's assume this is given to you that one word equal to 4 bit. So this bitmap I can represent into a sequence of words. Agree or not? Agree or not? This I can represent as a sequence of words. These 16 bits I can represent as a sequence of words. Correct? This I can do. For example, if your 16 bits are like this, let's assume 0, 0, 0, 0, 1, 0, 0. Okay, let's assume 1, 1, 1, 1, and let's assume 0, 0, 0, 1, or maybe 0, 0, 0, 0. Okay, so in this situation, this is your bitmap, right? This is the bitmap. This is a bitmap, and you can represent like this. You can represent it like 0, and what this value will be? This value will be 4. This value will be in hexadecimal. You can write it in the hexadecimal. You can write it something like this. Okay, so something like this you can write. Okay, this is what I'm saying. So in the hexadecimal, maybe you can write. Okay, now you tell me. So if, okay, this is also the bitmap, right? This is also another way of writing the bitmap. And in this representation, of course, if I ask you, so what question can be asked? Let me tell you. So this, okay, basically this type of thing also can be done. Are you getting my point? This type of thing also can be done. Okay, agree? So basically, maybe sequence of hexadecimal words. Okay, hexadecimal, in hexadecimal. In hexadecimal. So this type of thing can be done. Remember, I don't know what question they will ask you in the GATE exam, but maybe they can ask you some question on this. Are you okay? Yes or no? Agree or not? Yes or no? Tell me. We don't know what question they will ask you in the GATE exam, but I am just telling you that they can ask you some question based on this, that they can represent the bitmap like this. Like one question, let me ask one question. Let me assume that you have many blocks. You have a disk, okay, with many blocks. There can be many blocks. Billions of blocks can be there. You have a disk with many blocks. Let's assume you have a bitmap. Let's assume you have a bitmap. Bitmap is there. Okay, so this bitmap can be anything, like, okay, maybe like 1011001101101011 and so on. So your bitmap can be anything. Okay, I'm not saying that which is your bitmap, but bitmap can be anything. Now let me assume that one word size is given to you, and that is maybe 20 bits. Let's assume this is given to you. Okay, this is a given. This information is given. And now the question is like this: how to find first, how to find first free block? How to find first free block? Tell me. See, one thing, if you find the first free block in the bitmap, then it can take a lot of time. Do you agree? Yes or no? In the bitmap, if you find the first one, then it can take a lot of time. Linear search you will have to do. For the first free block, linear search you will have to do. Correct? Do you agree? So if you find this, what I'm saying, if you find this first free block in the bitmap, okay, if you find this in the bitmap, basically find the first one. Basically find first occurrence of one. In bitmap. In the bitmap, you can find the first occurrence of, free block. So find first occurrence of one in the bit. So for that you have to do linearly. Correct? Linearly you have to do. It can take a lot of time. Do you agree? It can take a lot of time because linearly you will have to do. Okay. Now, what is the another thing you can do? What is the another thing you can do? The another thing you can do is this. Because this bitmap is given to you as a sequence of words. This bitmap is given to you, remember, as a sequence of words. So what you can do? You can just check whether this word is zero or non-zero. Okay. Basically, maybe you can use some hardware. That hardware will tell you that whether this is zero or non-zero. Let's assume for a moment, let's assume that you can very easily find out that one word, this word is zero or non-zero. That you can find out. Okay. In the question, let me assume that this information is given that finding a word is zero or non-zero is very easy. Okay. So finding a word is zero or non-zero. A word is zero. Remember, I am talking about the word. I am talking about word, remember. Okay, so a word is zero or non-zero is easy. It's okay, very easy. Then in this situation, what will happen? So let's assume, okay, so in this situation, what is the idea? You just tell me the idea. The idea is this. The idea is this. So on the bitmap, what you do? Just find out the word which is non-zero. Agree or not? Yes or no? In this sequence, what you do? You just find out the word which is non-zero. Find first non-zero word. First non-zero word. In that word, what you will do? In that word, then what you will do? Tell me. In that word, what you will do? Find the first non-zero word. In that word, what you will do? In that word, inside that word, you will find the first one. Right? Okay. Inside that word, you find the first one. Correct? Okay. Inside this word, find first one. So this is the idea. Is this clear to everyone? Okay, I'm not saying that. I'm just telling you actually this type of variation can be created. This type of variation maybe they can create. Some kind of variation they can create. Okay, let me know. Is this clear? So where will be your first block? Where will be your first block? You tell me the address of first free block. How to find that? The address of first free block. How to find that? Can anyone tell me? If bitmap is given in the form of words, address of first free block, if bitmap if bitmap is given as sequence of blocks, sequence of words, sequence of words. Okay, tell me about this one. How to find out? I want to find out address. Remember, I want to find out address of first free block. A number of first free block. Okay, maybe number of first free block I want. Just give me the number of first free block. So how to do that? Very simple. Let me know how to do that. So number of first free block I want, then what will be your formula? What formula you will create? I want number of first free block. Just give me the number of first free block. If bitmap is given as a sequence of words, so the answer is this. What you will do? Just skip all the 0 words, right? Okay, just skip all the 0 words. So I can say skip all the 0 words. So I can say number of 0 words from the beginning. Okay, see, this is a simple formula. What you can do? From the beginning, you can skip the 0 words. Let's assume this is a 0 word. So this is a 0 word. Then let's assume this is also 0 word. Okay, so like this. So let's assume this is a 0 word. This is also 0 word and so on. Okay, you skip these till the first non-zero word. Let's assume this is your non-zero word. This is your non-zero word. In this non-zero word, you do offset. This is your first one. This is your first one. So this is your first free block. Okay. And this is your first non-zero word. So your answer will be what? Very simple. Your answer will be that number of 0 words from beginning. From beginning, how many 0 words are there, right? Okay. Let's assume this data is given to you. Let me assume this data is given to you. Number of 0 words from the beginning multiplied by word size. Correct? Multiplied by word size plus this offset. Plus this offset. Correct? Plus this offset. Okay, plus offset. Is this clear? This formula, tell me. Let me know. Okay, anyway, some question can be created. Actually, maybe I'm just telling you this type of questions can be created. Are you getting my point? I'm not giving you the question because I could not find the question. Okay. So, but in the GATE professors, they are very intelligent. They can create some question based on this logic, because this logic is given in the books. In all the standard books, this logic is given. Okay, this logic, okay, one line logic is given. This 1 or 2 line logic is given, and the GATE professors, they are very smart. From one line, they can create one question. We don't know like how they will create the question, but maybe they can create a very beautiful question on this logic. But did you understand this? How to find the first block? So you have consecutive 0 words. This is a word. This is a word. So consecutive 0 words you have. From the beginning, how many 0 words are there? Multiply with the word size. What is your word size? You multiply with that plus the offset. That will give you the block number. Yes or no? That will give you the block number of the first free block. So this is another variation in the bitmap. This type of question can be created in the bitmap. This is what I'm telling you. Let me know. Is this clear? Very intuitive. Now let's see this. Another method is linked list. This method is another, that is linked list. In this, what we do? This method is also a very simple method. In this method, we do like this. Okay, let me assume this is free. 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 This is free block. This is free block. This is free block. Let me assume these are the free blocks. Okay. Now, how to keep track of the free blocks? Also, let me assume this is a free block. Let me assume this is also free block. Okay. So how to keep track of free blocks? So in the linked list method. Okay. So basically, keep track of free blocks. How to keep track of free blocks? How to keep track of free blocks. One method we have seen, that was bitmap method. Correct, right? Okay. So one method, bitmap method, we have seen. Now the method we will see is linked list method. Linked list, or I can say free list method. In this method, what happens? It happens that, very simple, you create a linked list of the free blocks. Yes or no? Are very intuitive, very intuitive. So you create a linked list of the free blocks. So let me tell you, in the linked list also there is way one. In the linked list, in this method also, in the linked list method also, there is a approach one. What is the approach one? What is the very basic approach that is coming to your mind? You tell me. What is the basic approach that is coming to your mind? Like, what is the basic approach? Very simple. That what you do. Okay, in every free block, you put a address of the next free block, right? Yes or no? This is coming to your mind, correct? So in this free block, you put the address of this free block. In this free block, you put the address of this free block. In this free block, you put the address of this free block. In this, you put the address of this. 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 This is a very basic approach that is coming to your mind. And what we do, this how many of them we have to put in the main memory? How many of them we have to put in the main memory? Only the first one. Okay, and what you do, this you put in the main memory. Correct? This you put in the main memory. This you put in the main memory. Is this clear? Only the first free block you can put in the main memory. Okay, only first free block you can put in the main memory. So this is approach one. Now this approach one has a lot of disadvantage. What is that? See, can you clearly see the disadvantage? This approach one is very stupid approach. This approach one, what is stupidity in this approach? In this approach, what is the disadvantage? And this is a big disadvantage actually. So what is the disadvantage? The disadvantage is like this. This is your block. See, this is your block, and what you are using it for? You are using it just to put one address. This is your block, and you are using it just to put one address. So how much waste? This is wasted. This space you are not even using. Agree or not? This space you are not even using. For example, let's consider this is your block 0. Let's consider this is your block 0. This is your block 1, block 2, block 3, block 4, block 5. This is your block 5. Now what you are doing? This is your block 1. Correct? This is your block 1. In the block 1, you are putting one address. The address of block 5, you are putting only one address you are putting. So this space you are not using. Yes or no? This space not used. We are not using this space. So what is the better approach? So this approach we don't use actually. This approach 1, this is not used. So we don't use this approach. What is the second approach? The approach 2. For the same question, what is the approach 2? In the linked list, this is the approach that we use. In the linked list method, we use the approach 2. Approach 2 is what? Approach 2 is like this. Approach 2 is like this. What we do? In this block, we put all the free blocks that we can put. Okay. Yes or no? Okay. What we do? In this, let me assume that one block can put 3 address. Let me assume. Okay. Let me assume one block can put 3 address. Okay. So let me assume one block can hold 3 address. One block can hold 3 addresses. Okay. Is this clear? Let me assume that one block size can hold 3 addresses. Is this clear to everyone? One block can hold 3 addresses. Assume one block can hold 3 addresses. Then what you can do? You can put this address also here. This address you can put here. Agree or not? Very simple. Okay, so this address you can put here. what you can do, this address also you can put here. So 3, okay, so this address also you can put here. Now, okay, what you will do now, so this address you can put here, this address you can put here, very simple. Then what you can do, then you can put this address, then you can put this address. So 3 addresses you can put. So these 3 addresses you can put. Now what you can do, now very simple. Now in one of them, okay, remember, so you can put this address in this block you have 3 addresses. These 3 addresses you have in this block. Okay, now one of them you can choose, maybe first one or last one. Okay, so one of them you should be consistent. Like, let me assume that I'm choosing the last one. So in the last address, in this also three address gets 3 address I can put. So in this also I can put 3 address, right? Yes or no? Is this clear? So in this also I can put 3 address. So I can put this address, I can put this address, and I can put this address. Then again, what I can do in this, again I can put the next free block address. Is this clear? See, this is a very, I can say, smart approach. It looks like a smart approach. So this is your approach number 2 in the linked list method. So what we do in this approach, this is your block. Of course, it was free, but now it is not free. Tell me, here, you tell me one thing. One question I want to ask you. What is that? Is this a free block? Is this free block? Is this a free block? Now this is not a free block. Yes or no? Now this is not a free block. Agree? Because now you are putting some pointers. Now this is not a free block, but it was free block. It was free block. Okay, yes or no? It was free block. So anyway, we are using only free blocks. Are you getting my point? We are only using free blocks. We are only using free blocks. So it is still available for us. Agree or not? It is still available for us. Maybe we can use it. Of course, before using it, maybe we will want to use these. Okay. So what I'm saying here, this is what I'm saying, that in one block, this is your block. In this block, what you can do, you can put multiple addresses. For example, maybe block 1. In block 1, you can do block 2, block 3, block 4. These you can put. Then in the block 2, what you can do? In the block 2, you can put more. For example, block 10, block 20, block 27. Like this. Okay. So like this you can do. Is this clear? And in this block, let's assume in this block 10 also, what you can do? In this block 10 also, you can do that. For example, block 100, maybe block, does not matter. The order does not matter. That is the reason I'm taking this example like this. Okay, and so on. So this is your approach. Is this clear? So you can notice this is your, okay, and this we put in the main memory. This you can put in the main memory. You can easily notice that we can access this also by this, correct? So we can access this also, and we can access this also. Okay, so like this. So this is your approach. Let me know, is this clear to everyone? So this approach too is what we use. Tell me, is this point clear? What is happening here? Okay, so we are only using the free blocks to keep track of free blocks. So if you have free blocks, then what you can do, you can take one free block. In that you can put some, okay, all the free blocks. How many free blocks are there? Then if more free blocks are there, if there are more free blocks, then you can take one more block. In that block, you can put more, like that. Is this clear? Let me know. Tell me, is this point clear? So like this you can do. Okay, so you can read this very, very easy. So here you can notice, store the address of n free blocks. Remember, store the address of n free blocks in the first free block. Now, the first n-1 of these blocks are actually free, and the last block will again contain the address of another n free blocks, and so on. So it is like this. What you do, you put 3 blocks here, 3 free block addresses you put here, 3 free block. Now you can notice these are actually free. These are actually free. Okay, these are actually free, and this was free. This was previously free. But now what you can do, in this also you can put some more addresses. Okay, but anyway, these are free blocks. So this is the idea. So you can notice the first n minus 1 blocks, these are actually free, and the last block that again contains n more free blocks, another n free blocks. So this is the idea. This is the idea of linked list method. So this consists of using a linked list of disk block, each block holding as many free blocks as possible. Yes or no? This is your approach to agree or not? Okay, each block holding as many free blocks as possible. Every block is holding as many free blocks as possible. So this is the approach. You can see this photo. In this photo, you can see what this approach is. Okay. Now let's move on. Let's solve some questions. Tell me the answer for this question. Can you tell me? With 1 kilobyte block size is given to you, and block address size is given to you. Okay, like 32-bit disk block address you have. Each block on the free list can hold how many numbers of free blocks? What is the answer? So here you can easily see that. Remember, one address size is, your block address size is given to you. This block address size is given to you, that is 32-bit. And this is your block. This is your block. And what is the block size? The block size is 1 KB, 1 kilobytes. So how many addresses we can put? So number of addresses we can, how many block addresses we can put? Block addresses we can store. So that will be what? That will be 1 KB divided by, so you can call it 4 byte. You can call it 4 byte. So 4 byte you can divide here. So your answer is going to be 256 addresses we can put, right? Correct? 256 addresses we can put. 256 block addresses we can put. Remember, 256 block addresses. So these many block addresses we can put. Okay. So here, so each block on the free list can hold how many free blocks? So the answer will be what? That will be 255. The answer will be 255. Yes or no? Because remember, as I told you, this is your block. In this block, you put a free block. This is 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 a free block. So these are actually free blocks. These are actually free blocks. This is another block which contains more free blocks. This is another block which contains more free blocks. Okay. Again, this is another free block which this is another block which contains more free blocks. Okay, I hope this point is clear. Let me know. Is this clear to everyone? Okay. Tell me, is this clear? So remember, these are actually free. These are actually free. Here you can store the data. Okay, so tell me one thing. Can you store the data here? Here addresses are stored, right? Here address is stored. Address is there. Address is there. Address is there. Address is there. So these are addresses, correct? Here already you have block address. Here you already have block address. Correct? These are the block addresses. So can you, like, if I want data, can you store your file here? Tell me. Can you store your file here? Can you store your file here? No, you cannot store your file here, but you can store your file here. 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 Is this clear? So here you can store file. Okay, here we can store file. We can store our file. Okay, so this is the idea. So here final answer will be 255. These many free blocks you can store. Is this clear? Let me know, because one address is occupied. One address. This one address, it is for a block which contains free block. Okay, so your final answer will be what? That will be 255. Okay, so you can clearly see that answer will be 255 free blocks, because one slot is required for pointer to another block. Pointer to next block which contains free blocks. Pointer to next block which again contains free blocks. Okay, is this point clear? Is this point crystal clear? Please tell me. Anyone has any doubt? Now let's see this question. Tell me the answer for this. When does linked list of scheme require fewer blocks than bitmap? When will it happen? When will it happen that this scheme will require fewer blocks than this scheme? When will it happen? See, this is always fixed, right? Okay, how many blocks it will require, that is fixed, correct? Fixed. Like this is fixed. How many blocks it will have, correct? Yes or no? Do you agree? How many blocks it will have, that is fixed. Fixed number of blocks it will have. Okay, so this will have fixed number of blocks. This is fixed. But when your linked list is going to take less number of blocks, when your linked list will take fewer number of blocks, when you have few free space, yes or no? When you have few free blocks, agree or not? If you have few free blocks, then it will take less space. Is this clear? If you have few free blocks, remember what is happening here. If you see the free list, if you see the linked list method, if you see the free list method, what we are putting in one block, in the free list method and in the bitmap method, here on one block, what we put address, right? We put an address, correct? We are putting an address. This address we are putting, free block address we are putting. Then we are putting another address. Then we are putting another address. Then we are putting another address. So like this, we are putting the addresses. Okay, this is another free block address. This is another free block address. But in the bitmap, what we do? In the bitmap, we just put one bit. Okay, we just put one bit. So here you can notice this is one bit for one bit for a block. For a block, one bit you have. Naturally, what do you think which will take more space? What do you think which will take more space? What do you think which will take more space? Yes. So it looks like generally, okay, generally it will take more blocks. Generally here number of blocks will be more. Generally this will happen that here number of blocks needed. Here number of blocks will be greater than number of blocks needed here generally. Okay, this will happen. This will happen. Okay, like this will happen generally. But this will not happen, or I can say when this will happen. Tell me when this will happen. When you have less number of free blocks. See, here you have information of every block. Okay, here every block information you put. Every block. This bitmap does not care about the free block. Yes or no? This bitmap does not care about the free block. It does not care about the available block or occupied block, whatever. It does not care. So this will happen when few free blocks. If you have few free blocks, then what will happen? Then this will happen that you can have less number of addresses here. Very less number of addresses you will have here. But here you will have one bit for every block. One bit for every block you will have, right? One bit for every block you will have. So this is the idea. I hope this point is clear. So when few number of free blocks you have, then this will happen. Okay. So here I can say that here the answer will be few free blocks you have. Okay, so it means disk is nearly full, right? It means disk is nearly full. Few free blocks means disk is almost full. Disk is nearly full. Okay, now let's move on. Tell me this question. Does linked list method waste our disk space? Are we wasting our disk space with the linked list method? Tell me, anyone? Are we wasting our disk space with the linked list method? It is consuming disk blocks. That is a different point. But that, see, you consume some disk block. Let's assume you consume some space you are consuming, but are you wasting that space? Two questions. These are two different questions or not? You are consuming some space, but are you wasting that space? For example, let's assume you go to IIT, ISC, some top college you go. So you are going there. That is fine. But are you wasting one seat there? Are you getting my point? Okay. If you don't study, maybe if you don't do good work, okay, there, like if you are just wasting that, like maybe some other student could have used it. Yes or no? Maybe some good student could have used it. Okay. So this is what I'm some analogy. Anyway, what I'm saying, you are taking the space, that is fine. But are you wasting space? This is my question. See, interesting question. It is it is a very interesting question. Okay. So you tell me, this is an interesting question, that are you wasting space? You are taking space, but are you wasting space? So let me know. Definitely, if you're just tell me this point. Okay, I'm asking you two questions. Tell me the answer for this question. Disk is almost full. Now are you wasting space? Let's assume disk is almost full. Assume disk is almost full. Now does linked list waste space? So here the answer is no. Right? Here, how many blocks linked list will need? How many blocks linked list will need? How many blocks free list needs? Or I can say free list takes? Few. Okay, I can say few. Correct? I can say few. Agree or not? Very less. Because almost full you have. Your disk is almost full. Then I can say how many blocks your free list will take? Few blocks it will take. Now, okay. Let's see this question. Assume your disk is already nearly empty. Your disk is nearly empty. Now how much time how much space your free list will take? Now you tell me how many blocks free list will take? Tell me how many blocks free list will take? Many? Can I say many? Yes or no? But are you wasting it? You are not wasting, because your disk is already empty. You are not wasting because your disk is already empty. Are you getting my point? Your disk is already empty. So you can take as many space as possible. Your disk is already empty. You can take as many space as possible. This is not a wastage of space. Yes or no? This is not a waste of space. See, this is the benefit with the free list. The free list method, actually what it does, it takes only the free space. Yes or no? It only eats up what it eats. It eats up already free available space. Yes or no? Already free space. It was already a free space. It eats up that. Agree or not? Yes or no? You have already free space. It will eat up that. For example, let's assume you put a file. Okay. Your many free blocks you have. Many blocks you have. This free list is taking many blocks. Now let me assume you have a very huge file, very big file you have. You want to store it. Then what will happen? No problem. It will shrink. This free list, it will shrink. Yes or no? It will shrink. It will give the space to the new file, because when you store the new file, then the disk will become nearly full. Agree or not? Then you will go to this situation. So the disk will become nearly full. So you don't need more blocks for the free list. Is this point clear to everyone? Please tell me. See, very simple point. It's a very simple. It's like this. It is like this. Let's assume there is a train, the general compartment of the train. Have you seen the general coach of the train? Have you seen that? Okay, if you have ever like done this, so what happens here? See, let's assume it is empty. Your coach is empty. Then you can sleep like this is your berth. Okay, then what you can do? You can take as much space as possible. No problem. Yes or no? This is your berth. You can sleep here. Okay, yes or no? You can sleep here. You can sleep. This is you sleeping because the coach is empty. If your coach is empty, then you can sleep. Now tell me, if more people are coming, then what will happen? If more people are coming, then there is no problem. You will sit. Yes or no? You will give the space to them. Now you are sitting. Okay, now you are sitting. Are you getting my point? Now you are okay. Now you are not sleeping. So are you getting my point? Is this clear? Are you getting my point? What is happening here? See the free list, what the free list is doing. So when you actually need the space, it is giving you the space. It is not eating your space. Are you getting my point? The free list is saying, what the free list is saying, I don't eat your space. I am not eating your space. Okay. If you need the space, yeah, come take it. I don't mind. But the bitmap does not say that. Agree or not? If bitmap needs, let's assume bitmap needs 20 blocks. Let me assume bitmap needs 20 blocks. 20 blocks for bitmap store. Okay. Now it does not matter if you need these 20 blocks, then also it will not give you. Agree or not? Agree or not? If you want to store a file, okay, and you need these 20 blocks, then also it will not give you. This is fixed. This is a fixed. Okay. But here the free list will give you. If free list has 20 blocks, let's assume, and you store a file, then what will happen? Then free space will decrease. If free space will decrease, then this size will decrease. Okay. So if you see this size proportional to size proportional to free space. So you are not eating the useful space. Agree or not? This interesting point, did you see? Please tell me. This is an interesting point, that these free blocks, okay, are used to hold the free list. So basically, if you use the linked list method, if you are using the linked list method, then basically it does not eat up your useful space. Yes or no? It does not eat up your useful space. It is a very, very flexible. What it will say? It will say that this linked list method will say, okay, जहां पे भी जगह मिले या थोड़ी जगह मिले दे दो मेरे को. Yes or no? Okay, if you have some space, give me. If you don't have space, don't give me. Yes or no? Yes or no? Adjust kar lo. Something like that. So this linked list is very, I can say it is very very good approach, that what you can do, if you have space, give me. If you don't have space, I don't need. Very simple. Yes or no? Is this clear? If you have space, give me. If you don't have space, I don't need. Tell me, is this point clear to everyone? So remember, it does not waste your useful space. This linked list approach, it does not eat up your useful space. It takes space, I agree. It takes space, but it takes already free of space. Okay, so remember this point. You are taking some space and you are wasting some space. That is different. Like for example, you are sleeping and many small children, they are standing. Yes or no? Now you are ashamed to the world. Yes or no? Okay, many people are standing, and you are sleeping. Okay, maybe 5 people can sit, but you are sleeping. Because of you, these 5 people cannot sit. They are standing, you are sleeping. What is the better approach? The better approach is 5 people can sit. This is the better approach. So this type of people, they are taking the space and they are wasting the space. Okay, yes or no? But just think about it, that let's assume there are no people. The coach is empty. Now you can sleep. So this free list method, this is a very nice method, that what you can do, if you have a space, give me. If you don't have a space, I don't need. Tell me, did you get it? Free list, this linked list. Very simple. Okay. So it takes space. Remember, of course, it takes space. It will take space, but it is taking space from already free space. So there is no, it does not eat up your useful space. Okay. So in this question, what I can say, remember in this question, the question is asking about number of, okay, which will need fewer blocks. Are you getting my point? In this question, I am only talking about how many blocks you need. How many blocks you need. So this will happen when disk almost full. If disk is almost full, then it will take less space. Okay. So very simple. So here I am talking about the how many blocks you are taking. Taking blocks and wasting blocks, these are two different things. This is what I'm telling you. Again, I'm telling you. Taking blocks, you are taking some blocks, you are taking 20 blocks. That is fine. But you are wasting 20 blocks. That is not fine. The bitmap method is wasting 20 blocks. Agree or not? Bitmap, that bitmap method, that is wasting 20 blocks. Okay, this bitmap will take 20 blocks. Now, if you need 20 blocks, then also it will not give you. Yes or no? So it will sleep. This bitmap will sleep. Now, if small people, now if small children, women are standing, they will keep standing. Yes or no? He will sleep. This bitmap will not give space. Are you getting my point? So if the bitmap is taking 20 blocks or maybe 100 blocks, if the bitmap is taking 100 blocks, now you can't use these 100 blocks. But if free list is taking 100 blocks, or maybe if free list is taking 1000 blocks, and you need to store some data, when you store the data, automatically what will happen? The free space will decrease. When the free space will decrease, this this linked list, it will decrease. So when you put more data, more people are coming, then what will happen? This linked list, it will okay, before it was sleeping, now it will sit, now okay, so it will keep shrinking. So if more data is coming, it will keep shrinking. So it will give the space to the data. It is giving space to the data, but the bitmap does not give space to the data. Bitmap has 100 blocks. It will keep 100 blocks. It does not care about anyone. Data is coming, data is going. I don't care. I am fixed. Okay, I will take 100 blocks. I am fixed. But the linked list method, what it does? Okay, if data is coming, it will shrink. If data is not coming, if data is going, you are deleting the data, then it will expand. So basically, it is not eating your useful space. This is the final point. So which method is better? Tell me. Which method is better? Free, yeah, linked list method is better, right? Yes or no? So it looks like bitmap is good method. Bitmap is very, sir, I like the bitmap method. 0 1 0 1 0 1. Good. I can easily solve the questions very easy. Okay, it looks beautiful. The bitmap method looks beautiful. 1 0 0 0. Okay, so something like that. Okay, so the bitmap looks beautiful, but that is not useful. Okay, so this is the difference. Okay, and this happens in the coaching industry also. Like something that looks very good, but that is not worth it. Okay, if someone is teaching you only the easy concepts, just okay, just read the formula, just by heart the formula, solve 5 questions. Now you will understand it. Definitely you will understand it, but that is not worth it. Yes or no? You will understand that formula, you will solve those 5 questions, you will feel that I understood the topic, you will feel that, yeah, okay, this is God, okay, he's a perfect teacher, I understood everything. But remember, that is not worth it. In the GATE exam, you can't crack the GATE exam. The teacher himself has never cracked in GATE exam. Okay, so that teacher who is telling you, okay, he himself can't crack the GATE exam with his own content. If that teacher, that God teacher, want to crack the GATE exam, if he wants to crack the GATE exam, he has to watch Go classes. Okay, so this is the point. This is the ultimate point. Okay, so you can you can give them suggestions, sir. Sir, you have never cracked GATE exam. If you want to crack GATE exam, sir, you watch from Go classes, then you teach us. Okay, so anyway, the point is very simple, that this bit method, this looks beautiful, like 0 1 0 for every block. Okay, if it is free, then put 1. If it is occupied, then put 0. It looks very easy, but it is not worth it, and we don't use it in the practical life. Okay, it is not used. The free list, the linked list method is used because that is very nice. Okay, so anyway, let's move on. Now let's see this. So ultimately, Now let's solve some questions. Okay, and one more thing, just last point. If you want to create a file, then what you will do? Just very simple. Okay, very common sense. If you want to create a file, then what you will do? If you want to create a file, let's assume you want 20 blocks, then what you will do? Then you will find the 20 blocks, available 20 blocks you will find. For example, two here, then you will use them. Yes or no? Okay, and when you use them, then what you will do? You will delete them from the free list. Yes or no? Okay, are you getting my point? See, you want to create, like, this is the free space. Let's assume this is the free space. You want to create a file. If you want to create a file, then what you will do? You will find, okay, I want 20 blocks. So let me find 20 blocks. Okay, 2 blocks are here, 2 blocks are here, 2 blocks are here. Okay, let me take these 2 blocks, these 2 blocks. So you want to create a file, 20 blocks you need. Then what you can do? In this free space, you can find out 20 blocks you can find. Those 20 blocks you can use. Okay. Then when you use those 20 blocks, then what will happen? Now those 20 blocks are gone from this list. Okay. If this is a bitmap, then what will happen? If this is a bitmap, then what will happen? For those 20 blocks, you will put 0, 0, 0. Yes or no? So if this is a bitmap, then for those 20 blocks, you will put 0, 0, 0, 0. If this is a linked list, then what will happen? If this is a linked list, then those 20 blocks address you will delete. From this, you will delete those 20 blocks address you will delete, because now those 20 blocks are not free. Similarly, if you want to delete a file, let's assume I want to delete a file, then what I will do? If you want to delete a file, then free space will increase. Yes or no? Now the free space will increase. Now you delete a file and this is bitmap, then what you will do? You are deleting 20 blocks. You are deleting 20 blocks. Then what will happen? For those 20 blocks, you will put 1, 1 here. In the bitmap, you will put 1, 1 here for those 20 blocks. If this is a linked list, then what you will do? For those 20 blocks, you will put the address. Their address you will put, because now they are free. Okay. So this, did you understand this? Let me know. Very simple. Okay. So you want to create a file, you want to delete a file. Okay. These two things you can very easily do. Okay. So like this you can do. So you can read this. This paragraph you can read, everything is written here. So if you want to create a file, then what you will do? To create a file, we search the free space list. Okay, whatever free space you have, that can be linked list or that can be bitmap. Remember, when I say free space list, remember, when I say free space list, it can be bitmap also, it can be linked list also. Now, if you want to create a file, then you search the free space. In the free space, the required amount you take. Okay, this required amount of space you allocate, and then automatically what will happen? This space is removed from the free space. Remove this space from the free space. Similarly, when you delete a file, then what you do? This space will be added to the free space. Yes or no? This space will be added to the free space, because now that is a free space. So this is how you can do. You can create a file, you can delete a file like this. Okay, that's it. Now some standard questions, we will solve some gate questions also. Let's start with this question. Tell me the answer. See, remember, now for this chapter, for disk space management, for this chapter, we will solve the gate questions. Also, we will solve all the standard questions from the Galvin book, from the Tenenbaum book. Okay, there is a operating system by Tenenbaum. So those questions also we will solve. Tell me the answer for this question. Which of the following is a fixed size data structure? Which of them is a fixed size data structure? That is bitmap. That is a fixed size data structure. Now, if anyone asks you, see, now the next question I want to take, and the next question is beautiful. The next question is really beautiful, but actually, what is the point? The point is this. In the Go classes, why we study standard questions, why we solve standard questions. If anyone asks you that, okay, Go classes is just solving the standard questions. Go classes is not for gate exam. Okay, Go classes is on a different level. Okay, Go classes teaches on higher level. Okay, beyond gate level. So if this type of things, if someone says, if anyone asks you why Go classes is focusing so much on the standard questions, why they are solving so many standard questions, then you can show the following question. See, this is a question. This is a question from the Tenenbaum book. Okay, modern operating system Tenenbaum, 4th edition Tenenbaum. Okay, this same question as it is, without any word change, This question has come in the GATE exam in 1998. Without a word is also not changed. This question as it is, free disk space, this D bits, everything. Okay, this question as it is, this question has come in the GATE exam. This happens, let me tell you. And there are many questions. I can show you at least 50 questions I can show you which directly has been taken from the standard books. Like for example, in GATE 2013, there is a question in theory of computation which is taken from Peter Lynch as it is. In GATE 2013, recently, okay, GATE 2013, one question is as it is without changing anything. Okay, one question of theory of computation is taken from Peter Lynch's book as it is. Okay, so like that. So it happens many times. So because what happens, let me tell you, what is the reason? The reason is very simple. Those professors who will create the GATE exam questions, they teach the concepts, right? In IIT, okay, for example, IIT Kanpur, IIT Kharagpur. Okay, the professor who will create the questions for the GATE exam, he is teaching the operating system course in IIT. Okay, now that professor is following this book. That professor is following Tenenbaum. That professor is following Galvin. Okay, so these books the professor is following, right? So that professor, it is very high probability that that professor will create a question based on that standard book. In that standard book, some question is there. So there is a high probability because he is teaching the course. Okay, so it is very high probability that he will create a question from the standard book. From in that book, if some question is there, maybe he will modify that question, or maybe he will take the question as it is. Okay, so this happens. You think about the thought process of the professor. Those professors are very busy. Okay, so that is the reason like they don't have enough time to sit for 1 month and think about some question I need to create for the GATE exam. Most probably whatever they will do, if at any point of time, if they come across some standard resource, maybe some foreign university or some standard resource, if they come across this question and they find, oh, this is a nice question, then maybe they can give this question to the for the GATE exam. Yes or no? Maybe this can happen. So that is the reason you should definitely focus on the standard questions. Okay, let's see this question. So can you solve this question? Tell me. So this is your GATE exam question. Let's see this. Free disk space can be managed either by free list or by bitmap. That we already know. Okay, so you want to manage the free disk space you want to manage, then you can manage using free list or you can manage using bitmap. Disk address needs D bits. For a disk with B blocks, there are total B blocks. F blocks are free. State the condition under which free list uses less space than bitmap. Okay, this free list, it will use less space than bitmap. Can anyone tell me what is the answer? Think about this question. Very simple. The question is saying that you have B blocks. How many blocks you have? There are B blocks. Okay, this is the block address. D bits. This is the block address. Now, F blocks are free. Okay, so F blocks are free. Now, so in which situation the free okay, anyway, so tell me, just tell me this situation. If this is the condition, then what is the size of bitmap? How much space the bitmap will take? You tell me that point. What is the size of bitmap? For every block 1 bit. Okay, these many blocks you have, so these many blocks you have, so B bits will be taken. For every one block, for every block 1 bit will be taken. What is the size, or I can say what is the space taken by free list? How much space free list will take? Okay, what free list will do? What free list will do? This free list, it will store the only for the free blocks. So for F blocks, it will store their address. Okay, yes or no? It will store, remember, it will store addresses of free blocks. Addresses of free blocks. Okay, so what is the size? So that will be for F, it will store there. So these many bits, FD bits, right? Okay, so in which condition the question is asking, state the condition under which this will take. So this should happen. Basically, what should happen? This FD should be less than B. This FD should be less than B, right? Okay. So the question is asking under which condition this will happen. So can I write like this, that F divided by B is less than 1 by D? Can I say this? Okay, F divided by B is less than 1 by D. Tell me, what is this F divided by D? What is this? Free number of free blocks divided by all blocks. What is this? Number of free blocks divided by number of all blocks. Total number of blocks. That is the fraction of free blocks. That is the fraction of free blocks in your fraction of free blocks. Or I can say percentage of free blocks in disk. Agree or not? Percentage of free blocks. Fraction, or you can say percentage. If you multiply with 100, this will become percentage. Yes or no? So you can say either you can call it fraction or you can call it percentage. Or percentage of free blocks. So this fraction, this percentage of free blocks, this should be less than 1 by D. This is your answer. Okay, this is your exact answer. This is your exact answer. That what should happen? I can say that fraction of free blocks, what should happen? The fraction of free blocks, this should be less than 1 divided by D. This D is the block address. Where this D is the block address. This is the exact data. Yes or no? This is giving you the exact data. Like in which situation you will take less space. So this is giving you exact data, that the percentage of free blocks. I told you few or large. This is telling you exact. Yes or no? Do you remember I told you when linked list will take less space than bitmap? What I told you? I told you when your disk is almost full. Yes or no? Or I can say your disk is free space is very less. Free space is very less. This question is giving you exact how much. Yes or no? I told you that free space should be less. I told you that free space should be less. This word less I was using. But now this question is telling you exactly how much. So this is an interesting question, right? This question is giving you the information exactly how much your free space should be. So your free space fraction, your percentage of the free space should be less than 1 by D. This is your question. Tell me, is this clear to everyone? Let me know. Any doubt? Okay. Now, if this D value is also given, look at this question, this 10 mm question. Okay. In this 10 mm question, this another question is given that if D value is already given to you as 16 bits, now what can you say? What should be what the question is asking you? Tell me. The D value is given to you 16 bits. What the question is asking? The question is asking percentage of disk space that is free. Yes or no? Interesting or not? So if you multiply with 100, then that will become percentage. On both sides, if you multiply with 100, like on both sides, see, on both sides, F divided by B, if you multiply with 100, then what will happen? Then this is the percentage now. Now you can notice this is the percentage. Agree or not? Now this is the percentage of free blocks in the disk. So this percentage of the free blocks in the disk, that should be less than what? That should be less than 100 by D. That percentage should be less than this value. Okay. Is this clear? Let me know. Please tell me, did you get it? See, the question is asking that D value is given to you 16. The question is asking percentage of disk space that must be free. Okay. So this we already know that FD should be less than B. And you can notice F divided by B, this should be less than 1 divided by D. This is the percentage. If you multiply with 100, this would be less than 100 divided by D. So this is called percentage. This is the question is asking. So this would be less than 100 by D. And the D value is already 16. This is already 16 bits. Okay. So in this question, okay, so D value is basically 16. Okay, because that bits will be cancelled. So D value is basically your 16. So your, and remember, yeah, of course, because the D value is already, we have taken this D value is 16. Remember, this D value is given as 16. Okay, so finally your answer will be what? That will be, so this F divided by B multiplied by 100, this value should be less than 100 divided by 16. What is this value? Can anyone tell me what is this value? Anyone? 6.25. So your space, your free space percentage should be less than 6.25. So what I can say? I can say percentage of free space. How much would that? How much that should be? Percentage of free space must be less than 6.25%. Okay. So this is giving you exact data. This question is actually giving you exact data. This is the interesting thing about this question. This is the beautiful thing about this question. Tell me, did you like this question or not? This is your Tenenbaum question. This is the beauty of standard questions. Yes or no? This is the beauty of standard questions. All the standard questions, whenever you solve any standard question, then you will see this. This is the beauty. Okay, very beautiful question. There are two things in this question, and like this you can analyze. Remember this F by B. Okay, don't forget about this F by B. This is your fraction of free blocks, right? Okay, so this is your fraction of free blocks in your disk. How many? Okay, what is the fraction of free blocks? What fraction of blocks is free? So this is your F by B. So this is your question. Tell me the answer for this question. Next, this is another simple question. Tell me the quickly tell me the answer. A simple question from the GATEOverflow I've taken. A bitmap can be used to keep track of blocks that are free in a file system. Okay, so 1 KB block size is given to you. Disk size is given to you. What is the size of the bitmap? This is very simple. So first you find the number of blocks. That is your answer. What is the number of blocks? So number of blocks, that will be what? You have 40 GB hard drive. Okay, and block size is 1 KB. Every block has 1 KB. So this will be your number of blocks. So your number of blocks is going to be what? That is going to be 40 M. So 40 into 2 to the power 20. These many blocks you have. 40 multiplied by 2 power 20. Right? Okay. Next, what is the size? So these many bits you will have. So number of bits in the bitmap, what that will be? Number of bits in bitmap. Number of bits in the bitmap, that will be this. These many bits. Yes or no? So these many bits you have. In the bitmap, you have these many bits. So you can convert this into like whatever data you want to convert. Okay, so you can check it out. This will become, you can convert into byte. So this will become megabyte. Okay, and if you want to convert into megabyte, then I can say this will become 5 megabyte. 5 MB will be your bitmap size. Okay, so size of the bitmap will be 5 MB. Very simple question. Now let's see another question. Quickly tell me the answer for this also. Calculate the number of disk block. So a hard drive capacity is given to you 20 MB. Very small hard drive. Disk block address is 16 bits. This is the disk block address. Disk block size is 1 KB. The number of disk block that you need, okay, to store the bitmap, the number of disk block required to store all the free blocks using bitmap. See, this is just to confuse, right? Actually, all the blocks will be used because this is the bitmap method. So how many blocks you have? Tell me the number of blocks. You just tell me the number of blocks. What will be that? Number of blocks will be, so you have 20 MB capacity. This is the hard drive capacity, and block size is already given to you 1 KB. So the answer will be 20K, 20 into 2 to power 10. So these many blocks you have. right? These many blocks you have, because 20 MB is the size of disk, and disk block size is already given to you 1 KB. So this data will come to you as 20 into 10 to the power 10. This is your number of blocks that you need. Okay, this is the number. So what is the bitmap size? You tell me about the bitmap size. The bitmap size will be these many bits, right? So the bitmap size will be these many bits. These many bits. Okay, can you convert into byte? Can we convert this into byte? So what that will be? I think that will be you can call it, you can take 2 power 3. So it will be like 20 multiplied by 2 power 7 bytes. Right? Okay. So this will become these many bytes. But what we need? We want how many blocks are needed for bitmap? Okay, number of bitmap blocks. Number of bitmap blocks. How many blocks you need if you want this? How many blocks you need to store this? So that will be 20 multiplied by 2 power 7 bytes divided by what is the divided by your block size, that is 1 KB. That is the block size. So your answer that will come here. What that will be? Can anyone tell me? Okay, you have to take seal or floor. Tell me, you have to take seal or floor. You have to take seal or floor. Yes, you have to take seal. Okay, so you will take the seal value because we are finding number of blocks. So you will take here seal value. So that seal value will give you what answer? So you can calculate, this is 2 power 8. So this will be 10 divided by 8. 10 divided by 4. Okay, so the answer will be 3 blocks. So for this question, answer will be 3. Okay, this is another question that can be asked. Did you notice in this question, we don't care about the disk, this address size does not matter. Did you notice? This does not matter. This does not matter to the bitmap. Yes or no? This data is given just to confuse, because this data does not matter to bitmap. Bitmap does not care about it. Yes or no? Bitmap does not care about this data. Agree or not? This data bitmap does not care. Bitmap does not care about number of free blocks. Bitmap does not care about the address. Bitmap does not store the address. Yes or no? Bitmap does not store the address. This data is given just to confuse. Because remember, bitmap does not store the address. Bitmap will store 1 bit for every block. For every block, you will store 1 bit. These many blocks you have, so these many bits you will store. Okay, so remember, the bitmap size will be equal to number of blocks, these many bits you will store. That's it. So this is just to confuse. Next, let's solve this question. This is UGC NET computer science question in the December 2013. Can you tell me the answer for this? How much space will be required for bitmap? Actually, this question we have done. This question we have done in the beginning of the class. The answer was 332.8. Right? This question we have already done, because remember, very simple, number of blocks you can find. Again, the question is very simple. You can find the number of blocks. So number of blocks will be these many. This is the size of the disk divided by the block size. Okay, so this you can find. These many bits. Okay, remember, these many bits will be will be taken by the bitmap. So I can say bitmap size, what that will be? Bitmap size will be these many bits. So this divided by 512, these many bits. So you can calculate in KB. You can convert this into KB. You will get answer option A. So this we have already done in the beginning of this lecture. Okay, so the answer is going to be option A. Tell me the answer for this. Another very simple question. Disk has 80 GB space. The size of disk block is given to you. Number of blocks needed to keep track of using the bitmap method. Can you tell me the answer? Calculate this. We want number of bitmap blocks. Number of blocks needed using the bitmap method. to keep track of free space. What will be the answer? Calculate this. Yeah. So very simple again. Let's calculate this. So first of all, you find the number of blocks. Number of blocks is equal to 80 GB. This is the disk size divided by 8 KB. This is the block size. So finally, you will find the number of blocks that is going to be 10 M means 2 to the power 20. Okay, so this will be the number of blocks. Next, after that, so what will be your bitmap size? So what is going to be your bitmap size? So the bitmap size will be 10 into 2 to the power 20 bits. These many bits, right? For every block, 1 bit you will have. For every block, you are going to have 1 bit. Okay, so these many bits. So these many bits you need. Okay, anyway, finally, what is this value? If you calculate this in the byte, just calculate into the byte, then you will get 10 into 2 to the power 17 bytes. Okay, in the bytes. Now you can find out how many blocks you need. So number of bitmap blocks, what that will be? Number of bitmap blocks. So to store the bitmap, how many blocks you need? So 10 into 2 to the power 17 bytes divided by what is your block size? That will be 8 KB. So if you find this out, then this will become 10 multiplied by, so it will become 2 to the power 4. Right? So these many blocks you need. Correct? So number of blocks needed, that will be what? Tell me how many blocks you need. So that will be 160. 160 blocks you need for this. Okay. How many of you got this answer? 160, right? Okay. So 160 you will get. Very good. Now let's see the last question. This is the last question for today. This is another question from the operating system by Tenenbaum. Last question for today. This is a very nice question. A very beautiful question from the modern operating system book by Tenenbaum. Okay. So let's see this. Tell me the answer for this question. What the this is a very nice MSQ question can be created from this. Maybe in some mock test, I will put some similar kind of question with some variation, of course, some small variation definitely. Okay. So see this. What the question is saying, the beginning of free space bitmap, the beginning of free space bitmap looks like this after the disk partition is for, okay. But basically in the starting, this is the bitmap. Okay. This is the beginning of the bitmap. Like in the starting, this is the bitmap. This one means here, this one means the first block is used. So, okay, tell me which convention is used in this question? In this question, which convention is used? In this question, we are using 1 for you. Okay. In this question, remember, we are using 0 for free. We are using 0 for free and we are using 1 for occupied. So this is the convention we are using in this question, but that is given in the question. You can easily see from the question. This is a very beautiful question. Every information is given in the question. There is no ambiguity. There is no ambiguity. The question is saying that, okay, in the starting, this is the bitmap. In the starting, okay, the first block is used by root directory. So that is the reason this one is coming here, because this is used by root directory. The system, okay, see this. What the question is saying, the question is saying the system always searches for free blocks starting at the lower index block. So basically your system, like if this is your bitmap, then your system will search in this direction. Okay. Is this clear? The question is saying that your system is searching for the free blocks starting at the lower number block. Means your system will search like this. Your system is searching like this. Okay. Next, what the next is what this is saying. For example, if you write file A which uses 6 blocks, then what will happen? For example, if you write file A which uses 6 blocks, then these 6 will be taken by file A. This is taken by root directory. Okay, and these are free. And these are free. Okay. Now you tell me the answer for the first question. The first question is, show the bitmap after each of the following action. Okay, in this order we are performing the actions. For after every action you tell me the answer. So initially what you have? Okay, so what the question is saying? So after writing file A, so you have, okay, now you initially have this. So this is the initial situation now. This is the initial situation, that 1, then you have 6 ones, 4A, then you have some zeros. Then you have many zeros, maybe 9 zeros you have. Okay. So what the question, see, this is the initial, this is the root directory. Here you have the root directory. Okay. Here you have the file A, and these are the free space. These are the free space. Okay. You tell me now, when you do this, file B is written using 5 blocks. After A, what will happen? You are writing file B. Okay. Writing file B. You are writing file B using 5 blocks. So you will search in this direction. You will search in this direction. Remember, you will search for free space, right? Correct. Search for free space will happen in this direction. In this direction, you are going to search for free space. So